third installment of Comets. If you want to understand the historical context of comets up until about the Middle Ages, go ahead and go watch Comets of Doom. And if you want to understand comets up until about the 1800s, watch Old School Cometary Theory. Now we're moving into the modern era of comets and what we know about them. But first, a brief overview. Some correct ideas about comets have been known for millennia. For example, many people have been credited with the discovery of the anti-solar nature of cometary tails, but this information goes at least as far back as 635 AD, when Li Chunfang wrote about comet tails and how they always point away from the sun, and also mentions that comets shine not by their own light, but from reflected light. Mostly, though, comets were seen as mysterious disaster stars that bring about war, famine, and drought. Also death, lots of death. By the 16th century, your comets of doomsayers were becoming increasingly few and far between, but a lot of people still believed that comets are very large, in some cases larger and denser than planets, and therefore a legitimate threat to life on Earth, and also that comets might be coming from Earth. Europeans, and a big chunk of the Middle East, had a really hard time letting go of the comets come from Earth theory, largely because Aristotle had said that they were. Incredibly rich and influential in his own lifetime, by the time the Middle Ages rolled around, Aristotle was practically a saint. He was at least saint adjacent, and this resulted in him being possibly the most influential person in philosophy to have ever lived. Drown in your tears, Nietzsche. When it comes to space, that's very bad, as Aristotle got pretty much everything about astronomy wrong, including the idea that comets are coming from Earth. The idea that comets come from true outer space, beyond the Earth's sphere of influence, was fueled in large part by the Great Comet of 1577, which was recorded in a wide variety of places, including Japan, Europe, Turkey, and India. This proved that the comet must be very high, higher than the moon, and far away. But just because the comet of 1577 was widely considered to be farther away than the moon and coming from outer space doesn't mean that the comet's orbit was well understood. Tycho Brahe, for example, conducted an impressive study on the comet of 1577, getting Hegesius in Prague to look at the coordinates of the comet in relation to the background stars the same night Brahe did the same thing, 500 miles away, thus confirming it moved less than the moon in relation to the background stars and was therefore farther away from Earth than the moon. But he still maintained that the comet lived somewhere between the moon and Venus in his aesthetically pleasing yet incredibly wrong solar system. Nevertheless, placing comets far from Earth's atmosphere was one of the great achievements of astronomers in the late 1500s. By the way, Tycho Brahe wasn't even sort of the first person to suggest that comets were coming from outer space, but he was the most famous. In fact, Tycho Brahe in his own works mentioned a Persian astronomer, Abu Mashar, who 700 years previously had placed comets firmly in the heavens beyond even the planets. Basically, by the 1500s, most people were on the same page that although comets are a bit unnerving, they're probably not affecting us in any doom-tastic ways. And by the 1600s, most people were willing to accept that although comets are reminiscent of weather, they probably are not coming from Earth. One of the problems with studying comets is they're unpredictable. They come out of nowhere and then they flee, never to be seen again. Or do they? By the 1700s, astronomers knew that some comets return. Edmund Halley was not the first person to suggest that comets return for a swing about the sun, but he is the most famous. Halley's comet is bright enough that it was recorded a ton of times. In fact, Chinese astronomers have recorded every appearance of Halley's comet for thousands of years, from 240 BC to today, with the notable exception of its passage in 164 BC, which I researched for ages. I fall down these rabbit holes. I don't know what happened. Is this like the Napoleonic Wars and the asteroid gap? I have no idea, and I spent so much time on this. If you know, just send me a link, please. In 1705, Halley published a paper claiming that the Great Comet of 1531, 1607, and 1682 was in fact the same comet and would be back again in 1758. Halley did not actually live to be 102, and so never saw the return of this great comet. But in 1758, it was observed again. Halley was correct. Comets return, and a returning object is a predictable object, and a predictable object is a studyable one. So while factually correct things were known about comets for millennia, disconnecting them from catastrophe really was the first step in understanding them. Because once you disconnect something from catastrophe, the question immediately goes from how do you avoid disaster to well, okay, if it's coming and going, where is it going? What is it made out of? Why do they look like that? And these questions start to become our modern understanding of what comets are. Like many astronomical objects, a better understanding of comets coincides with better technology, in this case, bigger and better telescopes. Up until the 1800s, comets were mostly depicted using only the naked eye, but now astronomers could draw them while looking through a telescope, illustrate them more up close, and get a good idea of their true nature. And sure, telescopes had been around for a while, but when Edmund Halley saw Halley's Comet in 1682, the biggest telescope in the world would have been something like 5 inches. 5 inches! You can buy a 5-inch telescope today for like $200, maybe $300. Hail John Dobson, patron saint of astronomy. Don't even get me started on Galileo's telescope. Every single telescope that you have ever looked through, no matter how crappy, has been better than what Galileo was using. Galileo was using the Commodore PET of telescopes. By Halley's Comet, 1835, people were ready. The 1800s were actually kind of the era of big, stupid telescopes, and because it was Halley's Comet, it was predictable, so people knew when it was going to show up. By their nature, most comets show up unannounced, drunk, and to the wrong address. Even with big telescopes, that kind of planning almost never happened with previous comets. So in 1835, a lot of people used telescopes to view Halley's Comet and then sketch what they saw. And this is where you really start to see the structure of a comet. People like Friedrich Bessel made incredibly detailed drawings, and you can see that he clearly saw the nucleus as well as the coma. Bessel didn't know exactly what the coma was, but he suggested that the comet's motion could be impacted by basically rocket-like thrusts. And in fact, cometary motion is partly determined by which direction the gas escapes from the nucleus. Halley's Comet 1835 wasn't the only 1800s comet to update humanity's understanding in the 1800s. Other important comets of that century were Comet Encke, Comet Biela, and Comet Donati. Let's start with Encke. Comet Encke was recorded in 1786, 1795, 1805, and in 1819 when Johann Encke finally put the pieces together and worked out that it was all the same comet and predicted its return in 1822. This was only the second predictable comet after Comet Halley, but Comet Encke had an advantage over Halley's Comet in that it returned every 3.3 years as opposed to Halley's average of once per human lifespan. Comet Encke still comes around, but it's just not very bright. It's no great comet of 1577. But recognizing that it was coming back every 3 years lent credence to the idea that comets are coming in and then running away. Basically, we can expect and predict the return of at least some comets, and it's harder to invoke a shadowy, malevolent nature when you're just so predictable. If Halley and Encke revoked Comet's mystery, Comet Biela revoked their gravitas. Quite literally. In the 1840s, it broke up into pieces as it flew near the sun. In the words of Agnes Clerk, the extreme lightness contained in each piece of the broken-up comet was evidenced by the fact that each piece didn't have any noticeable gravitational effect on each other at all. If Comet Biela was massive like a planet is massive, the two fragments should have at least had some interaction with each other. Those older arguments that comets could be just like planets or that Earth used to be a comet, Comet Biela was kind of the nail in the coffin for those theories. This didn't stop someone from blaming the Great Chicago Fire on Comet Biela, which is ironic because Comet Biela made it pretty clear that far from being colossal conveyors of calamity, comets are fragile and not made of very much stuff. About 20 years later, in 1858, a very bright comet flies into the inner solar system, and that is Comet Donati. Comet Donati was one of the great comets. It was the brightest comet of the 19th century, and large telescopes had been built at this point, so the technology to look at the comet's structure had really advanced. In fact, astrophotography had really started to emerge, and technically, Comet Donati was photographed. Pretty much as soon as photography was invented, astrophotography was invented. Unfortunately, even by 1858, the tech was so bad, the photograph of Donati looks like pretty much nothing. The picture, though technologically impressive, was really just not as useful as the sketches that were made at the same time. William Lassell made detailed sketches of the comet and recorded the apparent diameter of the nucleus, the diameter of the first envelope, and the much larger second envelope. The Reverend Dawes also drew the comet and noted the soft nebulosity or coma surrounding it. Obviously, Comet Donati wasn't the first comet to be seen through a telescope, and it wasn't the first comet to be sketched. So if it wasn't really a comet of firsts, what makes it so special? It was big, it was bright, and big telescopes had been invented. Basically, Comet Donati was a lot more accessible to a lot more people than any other comet had been up until this point. And what Comet Donati did was make it abundantly clear that there were parts to a comet. Instead of being just a fiery star, comets had heads, comas, a tail that stuck sticks straight away from the sun, and a tail that pointed generally away from the sun. Today we understand that there are, in fact, differences between the two tails. Okay, so every video I've ever made really runs into this problem eventually where it's like, how do I present this from a historical perspective? Because I think that narratively what we want is just, nobody knew anything about anything until one misunderstood super genius came along and changed the game, and then that just keeps happening and happening and happening ad nauseum until we get to the modern age. I cannot stress this enough. Never in the history of history has that ever happened. I could do a whole episode on things Galileo didn't do first, and it would include the falling balls experiment, inventing the telescope, and discovering a moon of Jupiter. And that's because history is always more complicated than we want it to be. For example, people are talking about comet tails streaming away from the sun because of pressure, at least as far back as Kepler, but the solar wind wasn't really understood until the 1950s and 60s. So it's not a step-by-step linear process, it's more of a big ball of hairy, waxy things coming together. For example, Daniel Kirkwood and Giovanni Schiaparelli proposed a relationship between comets, their orbits, and meteor showers in the mid-1800s. Cue a bunch of scientists trying to discover which comet goes with which meteor shower. A lot was happening in astronomy as a whole in the late 1800s and early 1900s. Astrophotography, spectroscopy, much better telescopes, the beginning of understanding electromagnetism and the solar wind and radiation, all of this was happening at the same time, but not everything became clear all at once. So by the time we get to the mid-1900s, the 40s and the 50s, a lot was known about comets, but there were still two really big questions. Number one, what is the nucleus made out of? And number two, where are they coming from? The theories that went on to gain real traction in the scientific community were basically happening simultaneously, which makes sense because how they look and act are constrained by what they're made out of, and what they're made out of is constrained by where they come from. Comets cannot live close to the sun for reasons. People have had some really random ideas about where comets come from. Why do we mostly never see comets, but then sometimes they just appear? It's a legitimate stumper. By the 1900s, people definitely knew that the reason comets seem to pop in and out of the sky was because they have these really elongated orbits and spent most of their time far away from us. Okay, cool, but then where are they coming from? A not uncommon theory was that planets make comets, and it's an old idea. According to Aristotle, Democritus and Anaxagoras thought that comets formed from a conjunction of planets. And even in the 1800s, some notable astronomers like Joseph-Louis de Lagrange still believed comets could come from planetary ejecta, or basically explosions from planets. And he wasn't even sort of the last astronomer to believe this. Sergei Sviatsky believed pretty notoriously well into the 1970s that comets were formed from the ejecta of planets. Of course, this wasn't the only theory about the origin of comets. Going back to the early 1800s, Pierre-Simon de Laplace said many correct things about comets, that they are not meteors, that they probably have no effect on Earth, that their tails are very thin, that they can't be very massive. He even likens the vapor of comets to snow evaporating. But Laplace also thought that comets came from the nebula between the stars that our sun and solar system then captured. This would make comets visitors to our solar system, not originating from within it. So what's happening? Does our solar system create comets, or does it capture comets? If it creates its own comets, is it continuously creating them? Where are they coming from? The current accepted view of the origin of comets is that they are old. They're icy remnants left over from the early solar system coming into the inner solar system momentarily from a gigantic reservoir of comets hundreds of thousands of times farther away than the Earth is from the sun. This is called the Oort cloud. Comets coming from far away doesn't just explain their unpredictability, it also explains how they look, specifically their comas and their tails. A comet, by its icy nature, can live comfortably for billions of years in the outer solar system, but when it comes into the inner solar system, it starts to lose its ices. This is what we're seeing when we see the coma and the tail. This is different from asteroids that don't have tails. They don't appear and then disappear. We know where Vesta and Pallas and Hygeia live. They're small, dim, and hard to find in a telescope, but they don't run away, completely disappearing from the sky for long periods of time. If comets really are icy bodies, they could live far away from us for a very long time, but not close to us because we're too close to the sun. The question, why do comets live in the Oort cloud far beyond Neptune, can be answered with, it's not that comets only formed far away during the early solar system formation, it's that all the comets that were too close to the sun are now gone. The only ones remaining live semi-permanently in the exurbs of the solar system. The Oort cloud is named after Jan Oort, who is not the first person to suggest that comets are coming from a giant reservoir far beyond Neptune, but he is the most famous. William Campbell alluded to an enormous supply of cometary material in the remote outskirts of the solar system in 1916. Robert Aiken referred to such a reservoir in which comets live far distance from the sun with elongated orbits that must take them thousands of years to complete in 1926. A year later, Armin Leuchtner talked about a belt of leftover debris farther out than Neptune, as well as near Jupiter. Ernst Üppig suggested that as a result of stellar perturbations, to a certain point, the farther away you get from the sun, the more comets there should be in the outer solar system. And finally, Kenneth Edgeworth, who wrote on comets in the 1930s, but whose ideas remained unpublished until the 1940s, probably because of his amateur status, said that it is not unreasonable to suppose that this outer region is now occupied by a large number of comparatively small clusters, and that it is in fact a vast reservoir of potential comets. From time to time, one of these clusters is displaced from its position, enters the inner regions of the solar system, and becomes a visible comet. They were all correct, although none of them made as detailed calculations as Jan Oort. Jan Oort is one of the very few astronomers to have seen Halley's Comet twice. He lived to be 92, and he saw it once when he was 10, and once when he was 86. In two papers, one in 1950 and one in 1951, he calculated that a cometary reservoir must exist between 50,000 and 150,000 astronomical units out from the sun, that this cloud of comets should contain roughly 100 billion comets of observable size, and that the total mass of the cloud should be on the order of 1/10 to 1/100th the mass of Earth. While the Oort cloud and the region it lies in is still not well understood, it's extremely likely that it exists, and that comets are in fact leftover icy remnants of the early accretion disk. They are not picked up from interstellar space, nor are they exhalations from planets in the outer solar system. Having said that, there's still a lot we don't know about the Oort cloud. Comets themselves are still very difficult to study. Okay, so now, what even are comets? They're big dirty snowballs, and I think we all know it, but how did we get here? Remember Comet Donati? One thing that's really clear, even if you look at sketches of comets from the 1800s, is that people could see through the comet's tail, and the coma looks very particleized. This sketch by a Mr. Wyville James Christie even shows the star Arcturus through the tail. So people have known for a long time that parts of a comet are breezy, they're fuzzy, they're particly. Well, pretty much everyone could agree that it's easy, breezy, beautiful particles. Is it particles all the way down? What about the nucleus? The idea that comets were particles all the way into the nucleus was very common, well into the 1940s, and it's sometimes called the flying sandbank model. It can be summed up by this 1945 quote from Henry Russell. The accepted view of the nature of comets is that they are loose swarms of separate particles, probably of very different sizes, separated by distances great in comparison with their own diameters. One of the most influential proponents of the flying sandbank model was Ray Littleton, who suggested in the late 40s and early 50s that comets were in fact loose aggregations of widely separated dust particles. Some versions of the flying sandbank theory have the mass of particles staying together under gravitational coherence, and some variations of the theory have each particle of the comet describing a separate independent orbit around the sun. But that idea didn't sit well with one Fred Whipple, who basically just kept saying, look, the idea of a totally particleized comet, those physics just don't work. Among his problems with the sandbank model were, there's so much visible loss of gases in a comet that the gas-to-dust ratio, or the gas-to-meteoric material ratio, could not be sustained if the comet nucleus was just a bunch of particles. Whipple argued that Littleton's theory could only be correct if the gas loss is being overestimated by a factor of at least 100. Basically, there's a lot of gas coming out of comets, and that gas has to come from somewhere, and that somewhere has to have mass. And if there's more mass, there's more of a reservoir reservoir for that gas. That mass is going to be higher if that something is a solid, and therefore a solid or mostly solid cometary nucleus would act as a larger reservoir for all that gas to escape from, which would be why we see the coma the way that we do. An icy body would fit the bill pretty nicely. You could in fact have quite a packed hard nucleus, but mostly made out of things that will sublimate under enough heat or pressure. This is very different from saying that a cometary body is mostly made from tiny dust particles that get blown back from the pressure of the sun. Another problem is the motion of comets. Comets do speed up and slow down over time. Some of that is gravitational perturbations from flying too close to planets, and gravity has an effect on everything. Whether the cometary nucleus is rock, ice, special material, solid, or particleized, gravity will have an effect on that body. But comets change their motion so much, it can't just be explained by gravity. But you know what could help explain their changes in motions? Jet action from sublimating gases, or delays in heat transfer, which is more likely to occur in something that's changing. So again, an icy body fits the bill pretty nicely. Another issue is the lifespan of comets. Comets with solid icy nucleuses, as opposed to many particles, were also more likely to live longer, making something like Halley's Comet fairly plausible. Can you imagine a body of dust particles staying together for hundreds of thousands of orbits, coming into the inner solar system, passing Jupiter and the Sun, and never being torn apart? That kind of cohesiveness is more plausible with a solid core. Of course, comets aren't all that cohesive. Just like with Comet Biela, it's clear that comets can be ripped apart by flying too close to the sun. Comets aren't as sturdy as, say, a large metallic asteroid, but are they so flimsy as a body of loose swarms of particles? On a rip-apartability scale, you're looking for something between a meteor and a sandbank. The icy conglomerate theory of comets, often called the dirty snowball model, worked really well to explain the motion, the lifespan, and the appearance of comets. Now, there's a lot more going on in comets than just the ice that we think of here on Earth. It's not all H2O up there. It's mostly H2O, but carbon is pretty common. Oxygen, nitrogen, and a bunch of molecules based off those atoms, things like CO2, CHO, C2H2, have all been found in comets, but they're still ices that sublimate into gases. Our dirty snowball is just slightly toxic. So the icy conglomerate model, or the dirty snowball model, came out of the 1950s and 60s, and it's basically the concept that we have of comets today. But even in the 70s, Littleton could not even with Whipple. In a 1972 paper, he wrote that the sandbank theory is good, actually, and it seems that it is only in recent years, in disregard of a century or more of observational material concerning comets, that any other view has come to be entertained. He said that Whipple's icy conglomerate model was not only wrong, but that the observations were manufactured specifically for the theory, noted that trying to land on a cometary nucleus might turn out to simply be a search for a simulacrum, and that the nucleus model calls to mind a child's toy train instead of an actual functioning machine. He ends the paper by saying that even if a probe lands on a cometary nucleus, and a nucleus is found, that is, even if Whipple's theory is correct, then in that case, the fullest credit must and shall be given for the imaginative insight that has led to the proposal being conceived, and for the skill in presentation that has led to its being received with such unqualified acceptance. So, those are fighting words. To be fair to Littleton, it's not like all of his astronomy work just evaporated into the ether. He contributed to our understanding of the early solar system, stars, galaxies, and yes, even comets. But on the nucleus theory of comets, the icy conglomerate theory was more correct, and the flying sandbank theory just kind of fell apart. One of the things that's really interesting in that paper is that he brings up that in the not too distant future, we'll send a probe to a comet, and then we'll see who is correct. Well, gentle reader, that's exactly what happened. Only a few years after Littleton's denouncement of the icy conglomerate model, a probe called IC3 was launched. Although it was originally built to study the solar wind, in 1985 it made the first spacecraft flyby of a comet, flying through the tail of comet Giacobini-Zinner. ICE took the measurements of the composition of the comet and found that the constituents of the tail backed up Whipple's model pretty darn well. Only a year after IC3 flew through a cometary tail, Halley's Comet was due back around, and countries with spacecraft, they were ready. Russia sent 2 probes, Vega 1 and Vega 2, Japan sent Sakigake and Suisei, and the ESA sent Giotto. Together these probes were called the Halley Armada. While none of them landed on the surface of a comet, they all got close enough to make important discoveries. Giotto got super close, within 600 kilometers of the nucleus, but, and I cannot stress this enough, this wasn't a competition between countries so much as it was a deep collaboration. And what did they find? Basically, that Whipple was right. In the May 1986 issue of Nature, the Vega team concluded an article by saying that the encounters with Halley all but rule out Littleton's sandbank model. And while they name-drop Whipple, they politely don't name Littleton, but they absolutely included his references. So the Halley Armada took a bunch of very 80s space pics that showed cometary nuclei are pretty solid. Giotto in particular showed the gases escaping what appears to be a solid nucleus. And while Whipple may have been right about the nucleus being an icy conglomerate, Comet Halley turned out to be quite a bit darker than anyone expected, leading scientists to wonder, are comets actually dirty snowballs, or are they icy dirt balls? In the case of Halley, probably the latter. So the Halley Armada took all of these photos, but none of the probes actually landed on it. It was almost 20 years later before a probe successfully landed on a comet, which was perfect for me because that gave me time to grow up and start paying attention. In 2005, NASA launched Deep Impact and sent it to Comet Tempel 1. It was a very exploding mission. Basically, the probe landed when an 800-pound piece of copper traveling 20,000 miles per hour was crashed into a comet. The resulting crater, dust cloud, and debris were all then studied. Honestly, the probe should have been called Deep Impact 2. Earth Strikes Back. The goal of Deep Impact was to investigate the interior of a comet, and a huge number of ground-based observatories collected data, as well as the Rosetta spacecraft on its way to Comet Churyumov-Gerasimenko. And what did the Deep Impact mission find? There was new material after impact that was compositionally different from that last seen before impact, so comets have layers. The ratio of dust to mass was higher in the ejecta. The most likely explanation is, yeah, there's some rock and dirt in a cometary nucleus. And after the dust settled, the comet's behavior was basically unaffected by a half-ton cannonball careening into it faster than a speeding bullet. A week later, the comet behaved pretty much exactly like it had before. So even though comets are light, they're not exactly fragile. I know I'm splitting hairs here, but Deep Impact didn't land on a comet so much as it shot a comet. The first soft landing on a comet, what we think of as a spacecraft landing onto another body, didn't happen until very recently. No matter how you do it, landing on a comet is very difficult because a comet is comparatively moving very quickly, and it's also comparatively very small. There is a reason that the first soft landing on a comet happened in 2014, and that first goes to the Rosetta spacecraft and its little friend Philae. So Philae actually landed on Comet Churyumov-Gerasimenko, which is named after Klim Churyumov and Svetlana Gerasimenko. The water vapor coming off of Comet Churyumov-Gerasimenko is deuterated water. It's deuterium, it's heavy hydrogen, essentially, is in the vapor, which means that comets are probably not great vehicles for getting water to Earth. It's easy to forget, because we're land animals, that Earth is essentially a water planet. Where did we get all this water? Well, one of the theories that people have had for a really long time is that comets were bringing water to Earth. Well, theories about that water coming from comets, it's no longer looking so good. Okay, so when Rosetta got there in 2014, before Twitter was just a giant dumpster fire, there was this Twitter account that the ESA had for Rosetta, and it was so cute. Basically, I got a Twitter account just to follow Rosetta and Philae because it came with this little cartoon, and it would tweet out things like, I'm awake now, and my little brother Philae is going down to the surface. And it was so freaking cute, you guys. NASA's whole shtick is basically, we're strong, we're brave Americans. And meanwhile, the ESA is over here just like, you want some cuteness overload? And the answer is yes. Yes, I do. Far be it from me to critique NASA, but you know what? Be cuter. Okay, so that basically brings us up to the modern age with comets. There's a lot to talk about that I didn't talk about, and also there's a lot more to learn because comets are still not very well understood objects because they're still pretty difficult to study. From a historical standpoint, comets really are outliers because in astronomy, it's actually pretty common for the truth to be stranger than fiction. That objects end up being far more impressive than previously imagined. They end up being bigger, hotter, older, farther away, more numerous than our minds can almost comprehend. In the Middle Ages, no one was saying, oh, but the sun is so hot it tears matter apart at the atomic level. Nobody was saying that the Earth was 4 billion years old. It's just such a big number. No one was saying that the stars are trillions of miles away. Maybe Aryabhata. The size of the Earth, the heat of the sun, the distance to the stars, the number of galaxies have all been increased since people started writing about them. So it's fair to say that in the field of astronomy, things often end up being more spectacular or stranger than previously thought. But in the case of comets, people believed in their magnificence. They wrote often how great and terrible and doom-tastic they were. Even in the 1900s, there were people who believed that going through the tail of a comet could poison you with cyanide, which is pretty good proof that even 100 years ago, people still believed that comets were capable of great and terrible things. Stories of their greatness and terribleness come from all over the world, making comets one of the only astronomical objects to have this magnificence revoked. Basically, this object that was thought to be grandiose turns out to just be a dirty snowball. Would you like to see my process? First, I look at the lighting and I go, this is bad. I'm not gonna lie, this is like my worst nightmare. This is why I never do this. I don't even know why I have anxiety. This is not live. Oh, can you imagine me on Twitch? I cannot. I cannot just be like, hey guys, this is good. Like, I can't. Correct things were known about comets for millennia. Oh my God. Oh my gosh, I miss the 90s. Comet Donati is the 1800s version of badger, 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 mushroom, mushroom. I was sober when I wrote this, so that has to go. You know what they say, a bad metaphor is like a quesadilla on a shipwreck.